Great, thanks. The TAC knowledge-based population slot filling shared task is a query-oriented relation extraction task where systems are given queries. They're given a list of slots which are just named attributes such as city of birth, employers, and so on. And then systems are required to fill these slots for these queries from a corpus of documents. And the TAC corpus is a few million newswire and web documents. So in this case, a system given the query John Kerry, looking for a fill for the slot member of, that is, organisations that John Kerry is a member of, might go out, look for a document, and find that John Kerry is the member of the Senate Foreign Relations Committee. And we'll come back to this as a running example throughout the talk. So I think it would be fair to say that slot filling is a difficult task. The shared task has been running for 6 years, and in TAC 13, the F-score for the top system was 37%, with similar results for this year. What's important to note is that precision for the top systems, for most systems, is higher than recall, and for the top 5 systems, the precision ranges from 9 to 40% greater than recall. Perhaps unsurprisingly, the best performing system also has the highest recall. And so it seems that precision may be easier than recall, and improving recall is critical to improving slot filling results. So prior work has characterized these errors at a high level. We take this further by pinpointing the source of every recall error that systems can make. And what I mean by recall error are candidates that are either lost in the slot filling process or that are never generated at all, and I'll talk about that more in a moment. This allows us to estimate upper bounds on recall for systems participating in the slot filling task. So before we can talk about how candidates are lost, we need to talk about how we get candidates in the first place. So how does a system decide, given a corpus of documents, that Senate Foreign Relations Committee is an appropriate span in this document to even consider to extract as a slot fill for John Kerry? Of course, a system could take every n-gram in every document and consider that to be a valid fill, but that's impractical and probably infeasible too. So in practice, systems typically apply named entity recognition as a standard starting point for extracting fills. Now, again, systems don't simply use every single named entity that they find in documents as candidates for slot fills, and they apply explicit and implicit constraints over these named entities. And it's these hard constraints that we're going to be analysing in this work to see where systems lose recall or can never gain recall. And I've said recall a lot. Obviously, recall and precision always exist in a trade-off. But the key difference between the two, and the reason that we're focusing on recall, is that precision can always be improved. If you have a downstream process, you can always knock out incorrect candidates for any system and improve precision. You can't improve recall in that way. If you lose a candidate, or you never generate a candidate at all because you're never considering it as something that could be generated, you can't recover that downstream. So to take a step back, I'm just going to look at a high-level view of a very general slot filling pipeline. So systems are given a query, they retrieve documents that may contain fills for that query, they generate candidates within that document that may be correct fills, and then they actually apply relation extraction or other processes over those candidates to produce results. We're just looking at the first part of this pipeline where systems actually generate candidates. We're looking specifically at the TAC 11 slot filling data. We're only analysing name slots. And the reason for that is that named entity recognition is quite well established. There are easily available tools for this process. And we simply want to generate candidates and then evaluate on that set without any further processing, thresholding, or so on. This means that we can't look at string slots because there's not really a general way for actually extracting these. So, for example, criminal charges in this case beyond gazetteers. And while dates are relatively easy to extract, they require normalization and further processing, so we don't evaluate on those here. We also don't evaluate on alternate names because they often appear in a different format in text. And so we're looking at 100 queries over 29 slots with 535 fills that we're looking for. We create an Oracle document set from the roughly 2 million documents of 1,500 documents, which contain the documents that we know contain at least one correct slot fill. This is just for evaluation purposes because obviously the recall is not going to be increased by documents that don't contain anything. We then process this using Stanford Core NLP for NER, parsing, and co-reference resolution. And then we define filters, and these filters define what named entities can pass through. And they're defined by we're using these to model how systems actually generate candidates. So for example, a system might generate all named entities. We use that as a filter. And all of our filters are based on standard approaches that systems take and methods in the literature for generating candidates. There are many more filters in the paper than I'm going to talk about today. There are others, like including document filters, where we don't look at named entities. But I'm going to focus on 3 that I think are interesting and worth talking about here. They are the use of named entity recognition itself, looking at the impact of using query fill pairs in sentences, and a little bit of discussion about the use of dependency paths as a feature for extraction. Now, this is a pretty typical pipeline that applies to most slot filling systems. However, it doesn't apply to every system. Of the 14 teams that submitted system reports to TAC 13 that actually describe their system, 11 of these explicitly fit this approach. That is, they generate their candidates via NER and then extract them after this process. In addition, 8 of these systems use Stanford Core NLP for named entity recognition at least, but usually for the whole NLP pipeline. And so we think while we're remaining general, our analysis does apply to most slot filling systems. So let's start with named entities. We generate every named entity in every document and return it for every slot for every query. As you may expect, that gives us a pretty high baseline, which is the upper bound on recall is the percentage on top. 90% upper bound on recall sounds great. Of course, it generates 500,000 candidates. And remember that we are looking for 535. 500,000 is likely too many for any sophisticated downstream process to actually deal with. Most of the 10% error is caused by just named entity recognition errors, as you would expect. However, there are some other errors. Coordination often causes difficulty in this case. So let's say we're trying to extract the slot fill Pasco County. We can't do that simply by extracting named entities from Pasco and Pinellas counties. In addition, there are some fills that occur within semi-structured data like HTML lists, which just get a bit broken with the sentence splitting and named entity recognition in this case. The next obvious thing to do is to require that slot fills are of an appropriate NER type. So prior to applying this filter, John Kerry could have city of birth Obama. So we do the obvious thing and require that the entity be of a type appropriate for the slot. So John Kerry's city of birth must be a location. Here I've highlighted in red the organisation so that we can focus on trying to fill our member of slot, but obviously every slot gets its appropriate types. And applying this is quite effective. We do lose a bit of recall upper bound, 2%. Persons are usually typed pretty well, but organisations, locations, MISCs are where most of the error is occurring. And of course, this is great because it cuts down a candidate set to 100,000. And 88% is a pretty good upper bound. Like that's nothing to complain about. The problem is that at the moment, we've just been talking about taking every entity in a document and returning that without actually grounding the query in the document in any way. And in practice, which I'll talk about in a moment, systems follow the typical relation extraction approach of taking a pair of entities in a sentence, one being the query entity and one being the fill entity. If systems were to use more whole document style approaches for slot filling, then they may be able to take advantage of this high upper bound, although it's not clear how those approaches would look. So as I said, queries need to be grounded in sentences and hence in documents. So we've now taken the query John Kerry and we've found a mention of John Kerry in this document. Now in this case, I've just done it via exact text match. We could generate aliases, we could do named entity linking or so on to actually find a mention of John Kerry in a document and in a sentence. And once we've found the reference in a sentence, systems then look in the rest of the sentence to find entities that can be extracted as potential slot fills. So here, John Kerry Congress, John Kerry Republican Party can now be extracted as candidates for member of. Now, typically systems will want to apply some form of in-document co-reference as well. So here we've now got mentions in the second sentence of John Kerry, and so we can finally extract the candidate Senate Foreign Relations Committee, which is what we're looking for. Systems don't have to use co-reference, of course, and some don't, and I'll talk about that more in a moment. There is a middle ground to those two options, and that is to use some subset of co-reference. Here we're looking at proper noun co-reference. Now, there's two ways that we've looked at proper noun co-reference in the paper. The first is simply to take the full co-reference system output and only accept proper nouns that are output. And the second thing we've looked at is applying a naive co-reference approach that we've had success with in linking, just to see what happened. And it got some quite nice results. And the way this naive system works is it takes entities as opposed to NPs as candidates for co-reference, and then uses a heuristically determined set of rules to match candidates. So John Kerry and Mr. Kerry would be clustered together because they both are persons with the same surname. And so we apply co-reference now and look at the results for that. Full co-reference gives us 8% lower recall upper bound. As you would expect, most errors are co-reference errors, different types, the usual things where nominal co-reference is more difficult and so on. There are some cases where where co-reference could never find a fill. So here with Chief Executive Peter Clark down the bottom, Chief Executive obviously indicates that Peter Clark is the Chief Executive of some organisation that was mentioned previously. However, there's no reference to that organisation in this sentence. No co-ref cuts out a lot of recall upper bound, down to 64%, but it does also cut the candidate set down from 49,000 to 18,000, which if you're using a sophisticated, expensive downstream process to actually extract things may be beneficial if it's going to get you better recall in the end. Finally, the naive co-ref approach actually seems to get back most of what systems need to find and is a bit of middle ground on the number of candidates generated. So finally, I just want to talk a little bit about dependency paths. And we want to look at dependency paths as a feature, and we're focused on this for a few reasons. The first is many systems use dependency paths as a feature, no matter what learning process they're using to actually extract fills. They're fairly discriminative and precise compared to other features, and they don't seem to have worked as well as might be expected. So the top team, for example, from TAC 13, didn't use dependency paths at all, or any syntactic features in their system. And we wanted to have a bit of a look at that and do some analysis on that. So where we're using dependency paths, we're using lemmatized, although the example's not, but that's fine. We're using lemmatized Stanford collapsed and propagated dependency paths. And so here from Kerry to Senate Foreign Relations Committee, we have a dependency path that may indicate something about him being a member of that committee, if we can learn that chairman indicates member. In the paper, we've looked at how the length of dependency paths affects candidate generation, and it turns out that it may be worthwhile only looking at short dependency paths. But again, that's another trade-off. But what we want to look at here is, given that we're using dependency paths as a feature, given a set of training data, can we ever learn whatever we're looking for? So given training slot fills, can we ever, using some training method, get to the target test slot fills? Now, the use of this feature actually creates an implicit hard constraint, and that is that if you have a dependency path, it has to occur more than once in your corpus. Because if it doesn't occur more than once, then it can appear in your training set, and that's not helpful because it's not going to be in your test set, or it can be in your test set, but it's not in your training set, so you can't learn anything about it. And so we add this as a hard constraint. As a filter, rather, non-unique. And you can see that by filtering out entity pairs that have unique dependency paths between them, you're cutting down your upper bound of recall substantially. Of course, this is just looking at unique paths, and there may be paths that only occur twice, and that's possibly not that useful either. So to see if we can ever learn anything about a particular dependency path, we treat this just as a bootstrapping task. So given a set of training data and some target slot fills, can we ever bootstrap between paths, that is paths in context with the pairs, and pairs to eventually find a correct slot fill? And how many iterations do we need to do that? And for each iteration, how learnable is something? So the training data we've used is the TAC 0910 results, which for our evaluation gives us about 4,500 training seeds, and then we bootstrap from those over dependency paths to try and find our test fills. We do this for no co-ref, and it turns out that the upper bound is 43% on this, but the training data actually does a pretty good job of finding everything in terms of recall. It gets 39% of 43% in a few iterations. What this means is that more training data isn't going to help improve recall in this case. We've pretty much found everything we can find anyway. And what needs to be done to make dependency paths a more useful feature is to use some sort of similarity measure, kernel-based approaches, distributional similarity, to make better use of those. Of course, if we're only using dependency paths as a single feature, then we're never going to find these things ever. If we're using them within a classifier, then the classifier might be able to find them via other features, but of course it would be great to actually be able to use the dependency paths as a useful feature to improve recall. So hopefully this talk has given some ideas on where to look next for improving slot filling results. Potentially, if whole document techniques are possible for extraction, then this could help improve system results. We found that the naive approach, naive co-reference was actually quite beneficial, and so perhaps using more task-specific settings of co-reference and other NLP pipeline systems may be appropriate, and a more sophisticated use of dependency paths is probably required to actually leverage them as a useful feature. And I'd encourage you to check out the paper for much more analysis and much more numbers. So, thank you.
So we have 5 minutes for questions and comments. Okay, so I'll start by maybe a suggestion. So I think this is really nice analysis, and to make it more comprehensive, maybe I think we should put document retrieval into the pipeline, because maybe in the 2011 data, most of the queries are not ambiguous, right? But for this year, we added some ambiguous queries, and if the system does not apply sophisticated anti-linking disambiguation, then it will mistakenly retrieve some answers or miss some good answers.
Yeah. Absolutely. I mean, I mentioned named entity linking, but that was more because we were using an approach that we used in it. None of these filters take named entity linking or disambiguation into account. In some ways, we cheated a little bit with that because the TAC 11 data doesn't, as you said, doesn't really have ambiguous queries, although obviously within a whole corpus there are things that are going to be ambiguous. But yeah, I think adding an additional filter that looks at, say, linking or clustering or nil clustering or disambiguation or something like that would definitely be useful.
Yeah, I mean, even for non-ambiguous queries, you said most of the systems use Stanford CoNLP for name tagging coreference, and I also noticed most of systems use ING for document retrieval, and they usually just get the top 100 documents as candidates, right? So maybe more attention should be paid to that step.
Yeah. In the paper, we used Oracle information retrieval for the most part. In the paper, we do look at what the effect of, say, just using exact matching of strings is. Definitely more analysis in that is worthwhile. It would be nice to see this analysis for every year for a range of different systems as well. Obviously, not just using the Core NLP pipeline would be nice, but there's a lot of manual analysis. So.
That's great. Questions?
Thank you for the interesting analysis. I have a question regarding using different syntactic parsers, not just one, which might have errors or missing links in it. Did you ever evaluate things just co-occurrence of interesting entities and versus the actual syntactic paths that can be found in your specific parser? Do you have any evaluation on the amount you lose just by using a specific parse?
I suppose the answer to that is that, those numbers aren't in the paper, but typically the numbers reflect the parsing numbers, like the parser performance itself. What is interesting, though, is that even if the parser makes mistakes, you don't necessarily actually lose candidates. It depends on if your extraction process can actually learn the parser errors or not. So nothing here except for this final bootstrapping process. I suppose the unique filter as well if there's a parser error. But we find that parsers typically make the same errors. So in terms of this uniqueness thing, it's less affected. But of course, if there's parser error, then it's going to cause issues here. And potentially the use of schema decisions and that sort of thing are also going to affect what you do.
Okay, any more questions? Yeah, so I also would suggest to look into these different genres, like discussion forum may have a lot of misspelling, and some systems have tried like misspell collection. And also, when you say a more sophisticated way to use dependent paths, maybe you should also look at the trigger phrases for different slots. Like a top employee, we usually rely on a large dictionary of what are the indicators of top employee. So depends on how much the coverage of those trigger phrases that may also affect the real call.
Yeah. Just on that specific point, obviously we've left out a large portion of slot fills. So I had on an earlier slide 56%. One of those fills, a title, which are job titles in this evaluation, is actually about 20% of the slot fills. But more than that, if you know the job title, then you know, you probably know if someone's an employee or not. Just have a slide here. So this is like the slot distribution for our evaluation. You can see the top slots are employees, members, and top employees. So if you know someone's job title, which comes from a gazetteer, you're probably going to be a long way to learning these things. And I think, actually, this is another particular area where there's a lot more work to do in actually extracting these titles. Coverage of gazetteers. I think we actually did some analysis of, say, gazetteer coverage for these things. And I think it gets about, a title gazetteer from Freebase gets about 50% coverage or something from final output. So there's a bit of a way to go with these gazetteers. And obviously, in terms of spelling correction and so on, we are just extracting things directly from text in this analysis. We're not doing any sort of normalization or anything. So there might be a little bit more recall to gain, but we think that the evaluation is pretty reasonable.
Great. Thank you again. Thanks for the nice talk.
Great. Thank you.